So I wanted to mention just real quick, we're not doing the study set now. The study sets are due at 6 p.m. Part of that was for my sanity, so I made it the same time for everybody in the class. And it also gives you a chance. Some people will come before class, some people will stay after class. There are some typos on my answers. So I have a disclaimer in multiple places. I do provide you the answers in parentheses as a gift, as long as you don't let them frustrate you, because your teacher makes typos. And so on number 2, this place value was off the decimal. It should be 0.0181. So if everybody's been frustrated, please just realize that if you're not able to get to an answer that I give you, just as long as you're showing your work, and then when I go over it, you can make corrections. The other questions, there were 2 questions that came up. I will be recording when I go over the study set. It is not, you can come and listen. So Christian had asked me yesterday, he wanted to come and listen and just take notes, and then you can leave. You don't have to stay, because I'm going to keep lecturing for the evening people. If you're not able to come, that's fine. It's not, for you guys, it's not part of your grade because you're in this afternoon group. I will upload it. It usually takes 1 to 2 hours after class for things to get uploaded, just because Zoom has to go through a whole thing, and then YouTube, and so you just need patience with that.
So just to clarify, when is the mandatory class? Because I thought that was Tuesday and Thursday, 6 to 8.
I don't know who's asking the question.
Oh, it's Perry.
So Perry, you are registered for section 70, and it says Monday, Tuesday, Wednesday, Thursday, 1 to 3. So
okay.
you're supposed to be here every day from 1 to 3.
Okay.
So if you're in section
Right.
70, the people who are in section 71, they're in the evening, and a lot of them work. And so their class, they only mandatory have to be here Tuesday and Thursday evening, even though I'm there every evening. So every evening I'm gonna go through the study set. You're welcome to come. You're also welcome to come and listen to me go through lecture again. Or like Damon's here, he's registered for the later group. Like some people are going back and forth between, like some days they come in the afternoon, some days they come in the evening, depending on their schedule. That's why I was like, I didn't know who was talking.
Okay.
Some people,
I think like in the intro video, when you were saying something about how we could go to the 6 to 8, that's what confused me, but I've got it now. I'm good.
You're okay. I'm confused too. This would be a lot easier if we could just be live on campus. But you'll be fine. Everything will be fine. The other typo on the study set is on the second page on question number 9. This is the concentration, I think, of the cyclohexane, if I remember. Yeah. If you actually solve, X is going to be 0.00175. And when you give a concentration, you should have a unit on it or a pressure. So sometimes it gets rearranged. So some people came in early today. The other thing I want to mention is I'm going to try to always be here by 12:15 for office hours. So a little bit earlier. And if we have to bump it up, I might be a minute or two late. I might be a minute or two early, but if you have questions, and again, I'll stay after. So the worksheet, the study set, I'll go over at 6. It is due at 6 o'clock. You get the 5 points as long as it's uploaded by then, and you did your work showing like that's what my work's going to look like. And even if you got an answer wrong and stuff, the worksheet, you can ask me questions. A couple people came early and already did it and went over it with me. All right. So let's go ahead and do it will all make sense in another day once we get into the swing of stuff. We were at the bottom of, so I wrote a note to myself because Juan asked me a question yesterday after class on your notes. So on page 2 of your notes, so if we go back, question number 3. so all of you on your notes from yesterday, question number 3. So again, when I give the answers, that's like me typing really fast. And I gave the wrong answer for the IBR. It should have been 0.312 molar. So I think that was one of the ones where I showed the whole setup. It looks like I did the whole setup and then I never, because of time. And so he actually had finished solving, and the IBR should be that, because you would have to go up and take the initial minus 2x. And what I did is I just gave 2x. So just make a note of that and go back. So it's a good lesson for all of us. I am actually human just like you, and mistakes. While I'm on this page, just a reminder, your lab on acidosis. So you have to make a change for 7 days. It's due next Tuesday. So if you haven't started today, you have to start tomorrow, because, yeah. And if you started yesterday, that's great. You can turn in early. It does have 3 parts. You also get to watch a video. Some people told me they already have watched one of those, and you make a recipe. If you have other questions, you can either ask now or during office hours. But yeah, my hope is that this class is more than just, okay, I learned how to do ice charts and how to do a bunch of math, that you get inspired to realize your body is an amazing gift and we should take care of it. And our body is amazing in that it can heal. It heals actually quite fast. One of the amazing things of being human. And diet is one of the keys to starting that. All right, we are on page 4 of the notes. We talked about Le Chatelier's. Another reminder is you want to be picking a famous chemist. You don't have to have it this week, but it will be 2 weeks from today that we will be doing our presentations, and I'll have a sign up. We'll have 3 different times, 2-hour time slots, and so we'll worry about that in another week. But yeah, you can dress up as your famous chemist, and so maybe you'll pick based on that. The other thing I want to mention is it was a question Christian asked me after class yesterday. These are bringing back questions people asked me after class. The lab, there is a lab, Le Chatelier's lab. The video actually was already, I think, uploaded on YouTube. I opened the folder on Blackboard. So when you go on Blackboard now, I opened it like at noon today. There is a week 1A and then a week 1B. Otherwise, there would have been too many things in week 1. And so week 1B is tomorrow's notes. So there is going to be new notes for tomorrow. And then the study set for Thursday and the lab that's due Friday. You can actually do Friday's lab today if you want, because it is Le Chatelier's principle. You watch me in lab doing the lab, and so you get to watch and you just fill out, it's Le Chatelier's principle, and you write down the colors that you see, and then you explain why that happened. And so it's 4 pages of doing that. So you can watch the video, stop it, make notes. I'm absolutely willing to, during office hours, to look over your lab. And so this was a question Max asked me yesterday, and it was about office hours. This is more for Major and Araceli also. Nothing is due Saturdays and Sundays like last term. On Friday, you have a lab due, but the labs you can absolutely do before Friday. So you guys can all have a 3-day weekend. If you get your lab done and in Thursday, it's going to be 101 degrees on Friday. So Friday afternoon, I'm going to be in my air-conditioned house. And so I am willing to do an office hour on Friday afternoon if people have questions. And so that would be like at our class time. And so we can talk about that on Thursday, because you'll know better then if you're going to be interested. The question Max had, I'm not going to do office hours on the weekend at all. I'm taking my weekends off too. But I can do an office hour on Friday if you want me to look over your lab on Friday afternoon while you're sitting in your air-conditioned house also, unless you like the 101 degrees. All right, we want to do this question though at the bottom of the page, and there's more practice with Le Chatelier's, And tomorrow's study set, half of it is math and half of it is kind of Le Chatelier's and more theoretical stuff. All right, so we have, and this is actually kind of like what the lab is. So you have a test tube. The idea of equilibrium is in the test tube or whatever, in the flask. It has to have a cork on it so the gas can't escape, but in there you have both the NO2 and the N2O4. They are both in there. For equilibrium to be established, they both are there. You don't have equal amounts unless K was 1, which it's very rare. I don't know if I've ever seen K equal to 1, but of course you could see that. You have them both there. The color you see is telling you if the equilibrium is shifted towards which one you have more of. So if you're looking at the test tube and it's brown, I used to be able to do this demo and then somebody broke the tube. And so I don't have this awful noxious gas anymore to do the demo. But you see brown, the tube looks brown. And if there's no color, you look at it and it's colorless, you have more of the product. So it's shifted towards the forward. So I usually just show arrows, but it just means it's shifted one way or shifted the other. For Le Chatelier's principle, you're already at equilibrium. They're both in there. It's just you have more of one or more of the other. And so it's really weird because as you're adding something, like you could be adding something that's brown. Like if I added more of the NO2, if I'm somehow able to siphon in this brown gas, Le Chatelier's principle would actually push it forward. And so as you're adding brown, the brown would just become colorless because that's what Le Chatelier's principle says. It's going to push it in the other direction. And so that's what the video on the lab is, hopefully that you get the idea. It's not like colors with paints where you mix things in paints and see colors. It has to do with chemical compounds have a color that is the compound. And so if whichever compound is the predominant one is going to be the color you see. All right. Another question some of you had asked, and it's like the first question on the worksheet. The value of K actually tells us something. So just a review from yesterday. This K value is greater than 1. So what does that mean about the equilibrium? You can look back a page. It is product favored, right? We can look back a page. K is greater than 1. It is product favored. That's just going to become innate to all of you, that when K is greater than 1, you have more product. So this reaction is product favored. All right. What this is telling us is when we increase the temperature, though, we decrease the value of K. So we went from 273 to 298. So as we heat it up, the value of K decreased. What that is telling us, if the K is decreasing, that means it's shifting which way?
To the product way, to the right?
It's shifting reverse. So let's think about this. This is a tough question. It just requires you to walk through logic. K is products over reactants. The thing that's hard on this question, K decreasing is the effect. What I'm asking you for is the cause. It's the exact opposite of what happened up here. Up here, I told you what's happening. You told me the effect. So I gave you the causes. You gave me the effect. What's happening on this question is I'm saying, okay, K decreased. I increased the temperature and I made K decrease. Why did that happen? And you're saying, well, it must have shifted in the reverse direction. High temperature made it shift in the reverse direction, and that caused the decrease in K. You ended up with more reactants. So as the reactants increase, the value of K decreases because the reactants are the denominator. Since it's always a ratio, you can ponder this one. And so now we have to go with that. Is there questions with that piece, or you can think about that? So as the temperature increased, it shifted reverse. We have more reactants now in this ratio. So the value of K decreases. So K is always a numerical value. So my question though was not that. My question is it exo or endothermic? So if I'm heating it up, it's shifting reverse. That must mean that the heat is over here. So as I add heat, when you heat something up, the reaction has to absorb that heat. So the heat is on this side, and as I add heat, it's shifting it reverse. So if the heat is on the product side, it's exothermic. Now this is back to the question, Juan, you had asked me yesterday, and this is, you each have to figure out, and I have to try to help you figure out how you want to think about this. Exothermic means that heat is exiting, or that heat is a product is another way of thinking of it. For these reactions, whenever we talk about exo or endo, the delta H, we're always talking about what it is for the forward reaction. So it's exothermic in the forward reaction. That would mean in the reverse direction, it's endothermic. But whenever I ask you, is it exo or endo, I'm asking in the forward direction. So one way is always exo and another way is endo. Temperature, heat, high temperature loves endothermic because endothermic wants to absorb it. So whenever you increase the temperature, it always absorbs that heat. It always moves in the endothermic direction, which is reverse, which makes the forward exo. You have to figure out, you're going to have to go back and walk through this question like in your own brain to figure out how your logic will adjust to that. There's different ways I can explain it. And all right, so let's take it the next step. Any questions with that? So it's exothermic. Heat must be on the product side. High temperature shifted it reverse, and that decreased the K. So the next questions, that was like question A. Question B is, what's going to happen when you put it on ice? Well, it's going to shift forward. I don't do lefts and rights because my screen is flipped because of the writing that I put on the board sometimes. But if heat made it go reverse, then ice is going to shift it forward. So when you put it on ice, you've cooled it down, and the nature of equilibrium is it wants to maintain the equilibrium. It wants to keep everything the same. So on ice, it's going to shift towards the heat because it wants to keep it at equilibrium. So when you put it on ice, it's going to, in this case, it moves forward. And so what color is it? It's colorless. If you put it on ice, it actually loses its color. It was the coolest demo. You probably find it on YouTube. It was just really fun because I used to, like 20 years ago, be able to do it, and then somebody broke it. Thankfully, I wasn't there because this is like an extremely toxic gas. All right, so this is part C of the question. If you increase the pressure, what color would you see? Pressure has nothing to do with temperature. So on A and B, this all has to do with delta H. For C, pressure and volume are always related. So if you increase the pressure, that means you've decreased the volume. You have less space. So you're going to move to the side with less moles. It's just like you and me. When we have more stuff, we want more space. So when you increase the pressure, you think of it as a life lesson. When there's too much stuff going on, get rid of all the extra stuff. So decrease it. We have to go to the side with less, which is forward. And that is the side that is colorless. This is one of the hardest questions we do because it's logic. And so you have to think through it. Is there questions with that? You see why I didn't do it yesterday at the end. All right. I really can't wait to be live again because on Zoom, everybody's so afraid to ask questions. I'm on page 5, unless there was a question. I have a note about the study set, but I already talked about that at the beginning. So we're gonna do, you guys remember doing Hess's Law back in Chem 221? Wherever you took your intro chem class, Hess's Law is awesome. And so we're gonna get to that, but we're gonna do Hess's Law with equilibrium. So forget about the thermodynamic stuff. It's similar, but not the same. We'll come back at the end of the term and do it with thermodynamics. By the way, Dr. Hess, he's a famous chemist. He's American. He got his, no, wait, I have to think about that. Gibbs is the other one. Gibbs we get to after your famous chemist thing. So Dr. Gibbs always shows up on a US stamp when they do famous scientists because he's considered, and most people have never heard of him. All right. So this is just the starting point question. That's our starting point equation. I just want to remind you a couple terminology things that will help. However I write the equation, this is your reactants. Whatever we start with, that is the left side of the equation. Here's my double arrows, and then this is the products. However it's given, that's how it's thought of. And a reminder, this is our value of K, and so here K is greater than 1. So what does that tell you about this equilibrium? It's product favored. So the terminology is kind of funky. So we're at equilibrium. The value of K is just saying there's more product than reactant. All right. So what I did now is I flipped the equation. So what was the products is now the reactants. And what was the reactants is now the products. So it's up to you if you want to write all this stuff down. I'll get the piece that you need, but it is good practice. If we write our K expression, remember K is always products over reactants. So if we do it for this first equation, the original equation, we have the HI on top squared, right? So the coefficient becomes the power. And then hydrogen and iodine are in the denominator. All right, so that's our K expression. If I was to write my K expression for when I flipped it, all I did was change the perspective that now the hydrogen and iodine are the products, so they're in the numerator, and the HI squared is in the denominator because that's the reactant. So my question is, what's the relationship between my original K, I'm going to call that K1, and my K, I'll say KR for reverse. So when I flip the equation, what's the relationship? Well, it's the inverse, right? So K of the reverse is just equal to my original K to the -1 power. That's actually what I meant to. We'll put it in red. The other way you can say that, you can write it like that, or you can say that's the same thing as saying 1 over K1. I want to write it both ways because sometimes you'll see me do it one way and sometimes the other. You've all taken math. You know those mean the same thing. I don't care which way you do it. So if on your handy dandy calculator you do 1 divided by 50.5, you'll get this value. So suddenly my K is less than 1. If K is less than 1, what does that mean?
Reactant.
It is reactant favored, and that makes sense. Here it's favoring the product, the HI. Here it's favoring the reactant, which was the HI. So, so this is important because remember when we do Hess's law, sometimes we flip the equation. When you do it with K's, it means you flip the value of K. Now, this is different from when we did it with delta H's because K is a ratio. And so that's why it's flipping it. All right, so one more. Here we double, or I doubled my original equation. So I just doubled everything. So I have a 2, a 2, and a 4. Now back when we originally learned Hess's law, you would double the value, but that's not what we do here, because if we wrote our expression for K for this equation, we're not doubling anything, we're changing the exponents. So when you make a change to the stoichiometry, you have an exponential change to K. So we would now have HI to the 4th power. And we'd have hydrogen to the 2nd power and the iodine to the 2nd power. So I called that K2. If we were comparing to K1, I didn't double K1. So when I doubled it, I took K1 to that power of 2. If I tripled it, I'd take the K to the 3rd power. If I cut it in half, what would I do to K? Take it to the 1/2 power or take the square root. And so that's all my answer is here, is I took the 50.5 and I squared it, and I get this number. So again, when you double it, this is going to become the exponent. And that's what you do to K. So I'm looking at what we're going to do here. I'm going to jump down to Hess's law, and then I'm going to let you guys try. We'll come back and try this one and this one. So let's go ahead and put it with Hess's law. So with Hess's law, these are the 3 equations that you're given. So these are given to you. And this is the one you're trying to find, the one with the question mark. And so with Hess's law, you guys remember this is where we add up equations to try to make them equal this final equation. And so we have like 5 different teachers for when you learn thermodynamics here. So you're going to all do it the way you have to just show how you get to it, but you can listen to my explanation. That what I do is I look for the piece back here that's in my final. This you cannot change. This piece that I circled, that is what we're trying to solve for. So I can't change that. The ones that are given, those I can change. And so I need just 1 HBr. And so here I have to cut this in half. So I'm going to have to cut everything in half so that I only have 1 HBr, which means what am I going to do to this K value? I'm going to take it to the 1/2 power. So whatever you do to the equation, that becomes the power that you do to the K. All right, now the 2nd and 3rd equation, it's the same idea because we only want 1 H and we only want 1 Br, right? So we're going to have to cut everything in half. However, I'm going to have to take it to the negative 1/2 power because not only do I have to cut it in half to get just an H, I have to flip the equation so that the H is on the reactant side and the half H2 is on the product side. So when you flip the equation, and that's what we end up with, is the Br and the hydrogen end up with the HBr. Everything has to line up so they're on the correct side. So we have an H plus Br, and you end up with an HBr. Everything else should cancel out. And I just want to remind you, this class is all show your work. So your celebrations, you're going to have to show me how the equations moved around. So my hydrogen, my 1/2 H2 and 1/2 Br2, if they're on opposite sides of the arrow between different equations, they will cancel out. This is a small piece of it, and I'll give a chance here. So this also would take to the negative 1/2 power. So another way of writing that is you can say we took the square root of K1, or here you can say I took 1 over the square root of K2. You can either write it how I did here to the negative 1/2. This is to the power. I should put a little caret to make sure. Or this is 1 over the square root of K3. So we have one more step. We add the equations together, we get to that. There's no adding for K's, it's a ratio. So to get to your final K, you're going to multiply. This is similar but not the same because we're working with ratios. So our final K is going to be the square root of K1 over K2 and K3 because they're all square roots. Or you can say K1 to the 1/2 times K2 to the negative 1/2 times K3 to the negative 1/2. It just depends. Some people like one way or the other way. And some students like to figure out what each number is and do it with numbers. Whatever you do, you get this crazy number. 2.7 e to the 33rd. My favorite part of this whole term, my son took 223 last term with Dr. Russell, and he was asking me, he's like, these K values don't make sense. And you should all kind of be saying that. K's are exponential. All they're telling us is the equilibrium laying, does it favor the products or favor the reactants? This value, it's the 33rd power. This is extremely, very product favored. Very, very. Right? In almost every other language except English, they repeat an adjective when they want to emphasize it. So it's very, very product favored. This thing wants to make the HBr, which makes sense because hydrogen not as a diatomic. Why would you ever even see that? All right, I'm going to pause. You can take a few minute break, or you can go and try example 1 and example 2, and I'll go over them in a few moments. So on example 1 up here, let's go with a blue. So this is our original equation, and we just want to figure out how I change the equation. So I cut it in half, right? I divided by 1/2. So what you're going to do to K is you're going to take my original K, so let's say K1, and it's going to be to the 1/2 power or the square root of it. And that's where I get this number, which is extremely reactant favored because that K value is really small. Because K is a ratio, these numbers always come out bizarre. And so, all right. And then on this one, we're comparing to our original equation. All I did was flip it. And so we're going to do 1 over K1, or you can say K1 to the negative 1. And that's where I got that value, which now is very product favored. So just real quick, this is another famous chemist throwing ideas out there for you. This is oxygen. And this reaction is saying, either way we look at it, the reaction wants to move towards the oxygen, right? Or here it's going reverse towards the oxygen. So my question for you all, what is the O3? Does anybody know the name of that molecule?
Ozone?
That is ozone. And so a gentleman who is like the greatest smile in the world, like rivals yours, Major. He's won a Nobel Prize for this. He's a really fun chemist to do. So I think it was the first Mexican to win the Nobel Prize, and it was in chemistry, and it was for figuring out the depletion of the ozone and what all went on with that. But the reaction doesn't want to make ozone to begin with, so it's all right. This one, we're trying to get to this equation. And so our first equation, we're going to have to double everything. And the way I recognize that, it's kind of a big picture thing. I just write off, so I need the 2 NOBR, and that's where the NOBR is. It's on the correct side. It's on the product side. I just need 2. So I have to double the whole equation, which means I don't double the K. I take it to the power of 2. So whatever you do to the equation, you're taking K to that power. Right, and then in my next equation, it's nitrogen and oxygen I need, but I need them on the reactant side, so I'm going to have to flip this equation. So we need nitrogen plus oxygen going to the 2NO, and so when I flip it, I would just take the whole K to the -1. And then we would have K1 squared. You can either say divided by K2 or times K2 to the -1. And that is where we get this value. And just one more time, I'm going to ask to get that ingrained in that neuron so you don't have to keep flipping through your notes. What's that value of K tell you about this reaction? Our final value of K.
Reactant favored.
Yeah, it's very reactant favored. So you can just say reactant favored, or your teacher's being silly today. I like the very, very reactant favored. Why did we lose that in our culture where you repeat adjectives? It's like awesome in other cultures. Do you do that in Egypt? Like repeat an adjective? Like somebody's really tall. In Sanskrit, you say tulo tulo. You say tall tall. Do you do that in Egyptian? Do you repeat?
No. Sometimes, but I only do it when I like to bring anything. I don't know.
All right. Questions on this page? All right, 5 pages. I'm going to turn if there's no questions. All right. And so now we're going to do practice for 2 pages. To make sure we have a stronger foundation. So this, yeah, a reminder, your worksheets are always not due until midnight. Because once I go over the study set, sometimes that will help you to be able to solve some of the problems on the worksheet. We're going to need an ice chart. No, we don't need an ice chart. So it says we mix. So when you mix something, that is your initial amount. So all those numbers that you mix, and just a reminder in case you missed when I said I did post, I opened the next folder for the second half of this week. We're going to finish these notes. We move on to acids and bases tomorrow. So there's a new set of notes for you to download somehow for tomorrow and Thursday. Right, this is my initial amount, whatever I mix. That's my nitrogen, that's my oxygen, and that's my NO. So we don't actually do a full ice chart on this one. I gave you all the initials, and if I give you all the initials, what type of problem is this?
Q?
It is Q. So you can write a note to yourself. If you're given all the initials, you're gonna do a Q problem, which is great. So I'm gonna give you a hint of what to do. You're gonna write your Q expression, which is gonna be the same as your equilibrium expression. And then you're gonna figure out which way it goes. To do B, you will need to do a full ice chart. Your initials are these initials, all of them. There is no 0 in this ice chart, but to know if it's going to go forward or reverse, I don't have answers on this. I have to find my answers, or I'm going to have to do it real quick. That's going to be the answer for this will tell you if it goes forward or reverse. I'm going to pause recording go ahead and try whatever you want on this page, or you can take a 5-minute break, and then I'm going to go through this whole page. So again, number 1A is a Q problem because you don't have any zeros. There's no zeros, everything's there. So you want to write your Q expression, which is the same as your K expression, products over reactants. So the NO squared. And if you got it, that was my answer I got. You can keep working on stuff, or you can sit back and listen. Times the nitrogen and oxygen. And we plug in our numbers. For our nitrogen and our oxygen. And your chart, I want to remind you of a few things. The chart does need to show units. That's key because the units in the chart all have to match. Which if we're given molarity or moles and liters, we need molarity. If we're working with pressure, like down here, will be in ATMs. And then we solve for Q, which we have here. And then the way I do it, so I can remember while I'm here on this virtual world, I write them alphabetically, K and Q. My K value is larger than my Q value. So K is greater than Q. So it's going to have to shift forward. So when it says in which direction does it shift, so you can write out a full sentence that says K is greater than, because K is greater than Q, the reaction is going to shift forward, or you can simply state this. Give your value of Q, and then you can just simply state that. I'm fine with that. So now we have a part B. So to do this, there are no zeros, but we have our initials from part A. I think in worksheet 2, this is, you have a question like this, where first you solve for Q, and we determined it shifts forward. So this is my plus 2x, and my reactant side is my minus x. It's a 2x again because of the coefficient determines the number in front of the x. All right, so my equilibrium, this is 0.234 minus x. And this is 0.00432 plus 2x. Another, oh, we'll get to that in the next one. All right, we write our K expression. It's the same as our Q expression. So on your study set, and especially on your worksheet, because the worksheet I look at in more clearness, the worksheet is a way for me to give you feedback more gently. So your chart, I need to see it nice and orderly. Again, you can do it on notebook paper. Please set it up so that we could follow it. State your K expression, and then we're going to plug in. And at this point, we're going to be solving for x. So you can leave the units out. And what was my K point? I can actually, I have to find my erasing pens again, so I don't have to keep crossing out like this. All right, so just to clarify something I mentioned yesterday, half of you have one of those like $200 calculators. Don't go and buy one, like TI-89 or TI Inspire. And so at this point, you would say, you'd put a little star and you'd say solved with a TI-89, let's say. And you would tell me x equals, and you're going to have two values. So, because you're not going to have any of the other work that's there. So you would give me both values. Usually one of the values is going to be wrong. Either it's going to be a negative, which you can't have a negative value. So you would you give me the two values, and then you tell me which circle the one you pick. If you don't have a TI-89, then you're going to go through the algebra, which means we have to get rid of the square. And so just a reminder, you would then, for some students, they'll do it on another piece of paper, and they'll just write a note, see attached piece of paper. And so if you're somebody who has like like me, TI 15, you could do it on their piece of paper and just write a note, see it on attached piece of paper. So if you take a square root of each side, you don't have to write this down. I'm going to walk through it because there's sometimes somebody who needs me to do that. I need to make, oh yeah. There is going to be a way for you to be able to get rid of the squares. There's only one time, it's on the second worksheet, and today we're going to go through a quadratic. So you get, if we keep going from here, like 0.0412, which we would then multiply by the denominator. And so the squares are both gone. You can do this as long as everything has a square on it. Then you have to combine the x's and combine the other sides. So you would distribute this to both of these pieces, right? You guys remember doing that? And then you have to combine the x's and combine the other ones and then go through the steps. I don't have the space here. I probably do on the back side somewhere. But once you solve, you're going to get that x equals 0.00261. Again, if you have the TI 89 or Inspire, you'll have two numbers. I don't want you to go out and buy a fancy calculator. I've actually found the students with those don't necessarily have a better score because you have to be able to put it in your calculator correctly. And there's so much number. If you have one piece wrong, you end up getting the wrong value. Right. So if you cannot do, if you have a little bit of trouble doing the algebra to get to this number, just stay after for an office hour or come early tomorrow or come at 5 o'clock. Yesterday, there was nobody was here. I was sitting by myself. So don't be shy. All right. I did ask for the NO. So we would then go back and we would take the 0.00432 plus 2 times x. And that's where I got this answer. And I think Pablo said he got that number too. Did somebody else get that number? Maybe. Nobody else got that number? Everybody get a different? Go ahead. Oh, okay. So we had 3 people got my number. So we can go with that must be the answer unless somebody has a question. All right. And again, if I don't give you enough space and you're showing everything like on like you printed, just put a note at this point and say, see work. Like instead of saying solve TI 89, say see work on attached piece at the end of your scan. The other quick comment I want to make, because if you submit, like, let's say you submit your worksheet on Blackboard, and then you come to an office hour and you want me to go over it, because sometimes that's nice. You can submit it on Blackboard and then I can pull it up on my computer and look at it, and then we can talk through. I always let you submit it a second time. It has to be submitted the second time before the due to get the full credit. But that is something you can do so that I can look at your work while you're in office hours and give you feedback on anything that you might need to fix. Right. On number 2, this happens on the worksheet. The first thing you have to do, it's not going to have a full ice chart, but this is like the one major you had asked me about. I think it was you. Actually, I don't remember now. This 5 grams doesn't matter. Why does the 5 grams not matter at all for solving this problem?
Solid.
This is a solid. This goes back to something I commented on yesterday, very beginning of the lecture. You see a solid or a liquid, you want to cross it out. It is not part of your ice chart. The amount you have doesn't matter. All right. So we have nothing. That means if we did an ice chart, which we will, just because it makes it more logical for most of you. These are zeros. The amount of the solid doesn't matter. So there's one like this on the worksheet. I can't now remember which number it was. So this is going to be X, and this is going to be X. So when we write our K expression, the solid doesn't matter. The solid's there, it just doesn't matter how much there is. It's a really bizarre concept to get used to, but that's just how equilibrium works. Because this is, again, concentration, and solids don't have a concentration. It's how much is dissolved or how much gas is formed. So we're just going to have that the K equals X squared, and we solve for X, which is this number. It's actually, I gave you a lot of room because most students do lots of extra stuff. Everybody tries to do something with the 5 grams. If we were in class, I would ask, how many of you tried to change the 5 grams to moles? Usually somebody will ask me, hey, Sherpa, there's no volume given. How can I change? How can I find molarity? How can I find the pressure? And then the question asks for the total pressure. So pressures are additive. So you would just have the pressure of the pH3 plus the pressure of the BCl3, which is X plus X. So 2X equals P total. And so it's whatever double that number would be. So it would be 0.00, sorry. Why do I have it written like that? It's 0.0865. A quick comment is this is a pressure. If you're solving for concentration or pressure, you need a unit. So pressure is ATMs. On number 3, there's no unit because it's a K value. All right, questions on number 2. It's actually, so keep that in mind. If you have a solid, that's like a wonderful thing. It means, okay, I can ignore it for solving with K. All right, on number 3. So we're talking about things mixed. So we're going to do ice. CS2 is 1.2 moles, and the Cl2 is 3.6. And it's in 1 liter, so we can just say per liter. So that's my molarity. It doesn't give me anything else initial. So these are zeros, which means this is going to be, my product sides are going to be the plus X, and this is going to be, the CS2 is going to be minus X. Biggest mistake that's made on this one. See that?
9 moles of the CCl4.
No, this says at equilibrium.
Okay, that's my bad.
Okay, I saw that. That's at equilibrium. This is a 3, so this is going to be minus 3x. So what Christian was pointing out is this is actually key, and it's something to be careful with. I think the very first question on your worksheet, the very first 2 words say you're at equilibrium. If you're at equilibrium, you're there. In this case, we had an ice chart. So for the CCl4, we have 0.9 moles. And we're still in the same flask, because that's the whole point of it. Something else to be careful of when you do your study sets and worksheets, the units. When you do your chart, you have to have units. They all have to be the same unit, which at this point in the class, we're dealing with molarity or ATMs. All right, so this column is completed. So X must equal 0.9 molarity. So we can finish our E. So this would also be, so in red is what was given in the problem. So this is also 0.9 because it's just X. This is going to be 3.6 minus 3X. So 3.6 minus 3X is going to also be 0.9, if I'm pretty sure. And then this is going to be 1.2 minus X, which is going to be 0.3. Yeah. The biggest mistake that is made on this one, the biggest mistake is right there, that 3. You have to remember that has to come from the stoichiometry. All right, so our chart is done. We have all our equilibrium stuff. The other biggest mistake that's made is rushing. You have to state your K expression, sorry. And that 3 is going to be, this chlorine is going to be taken to the 3rd power. That's actually really important. Anytime something has a coefficient, it becomes an exponential change in K. So any change that happens to chlorine has a big effect on K. You'd plug in your numbers, you would show that, and you would get a value of K. Now, this is a question that came up last evening. Somebody asked me. That value of K is still greater than 1. That means it is product favored. Now, as opposed to before when I was saying very, very product favored, it is, this one's only slightly more, so it's just slightly shifted. This is different from Le Chatelier's principle. Le Chatelier's principle, we're at equilibrium and we're going to shift it. Or like here, for this question number 1, the Q question, we mix the stuff and the reaction has to move forward. So it moves forward to attain equilibrium. In the case of number 3, the value of K tells us that K favors one or the other. So it's a nuance with the words. In this case, it's on number 1. If that helps you, the words sometimes help students. It move forward to attain equilibrium. In a Q problem, you were not at equilibrium, and I'm asking what happens. All right, questions on this page?
So if it gives you the equilibrium number for any of the molecules, that means that all of them will have, the X will be that, right?
So not quite. In this one it is, because it was a 0 initial, and this had a coefficient of 1. So the equilibrium amount was X. But what if this was 2 CCl4s?
Okay, so it would be to the power of 2. I mean, times 2.
So you have to be, and actually, your question's really good. So, and that's actually important for everybody. If you go back to page 2 in your notes, Pablo, question number 2 on page 2, we actually had that a situation like that. And so I gave you the initial and the equilibrium of the same species. And so that equilibrium amount was not X. We had to actually do some math here. So does that answer your question? So you have to be careful. Yeah. That's why I had to hesitate. In this problem was actually, yeah, it's wonderful. And sometimes that happens and you're like, that's great. The key is the ice chart and then looking at that piece. And the other thing that I can't emphasize enough, I recommend you guys get colors, that you do this in colors so you can, like how I'm doing, I'm like stating what's given in the problem in one color. And these were the pens, I just found them, but they ran out of ink. Somebody got me these from my other class. These are erasable pens. That's the brand name. I used to find them on Amazon. Somebody got them for me, and they write in color and they erase. And so or if you have an iPad, it's really nice.
Okay.
All right. Any other questions from that page? Last page for today. So percentage. Percentage shows up in the study set 2 and worksheet 2, which again, it's not due until 6 tomorrow. But tomorrow's lecture is acid bases, so we move on. So let's go ahead and make our ice chart. And so I know I'm making an ice chart because I mixed the iodine. So 0.5. And that's all that I mix. So that must mean the IBR is 0 initially. All right. Question that came up yesterday, the temperature, we get to ignore it. The only times you're not going to ignore it is if we're dealing with Le Chatelier's, which we are going to do on the next one, or if it's a gas law question, you're going to, on the worksheets, one of the fun things I get to do on the worksheets is you're going to get to see some things from previous terms. So you'll get to use some of the things you learned in 221 and 222. All right. So this one's interesting. So at equilibrium, 68% has reacted. So we would take our initial amount times the percent that reacted, or sometimes it will say percent decomposed or percent changed, and that will equal our equilibrium amount. So in this case, the percent is how much it changes by. So we would take whatever that is, 0.25 times the 0.68, and that will give me my equilibrium amount. Is this number 4? This is not number 4, Joy. All right, that's 0.17, and that's our molarity. So I'm sorry, that's not the percent that reacted, 68% reacted. That is my change. That's not how much I'm left with. So that's what I was going to try to say. If this had said how much was left over, that would have been your equilibrium amount, or 68% of the iodine remains at equilibrium. The reacted is 68% this is telling me my change. So the initial times the percent was my change. And back to the question Paul had asked, this is decreasing by X, and this is going to increase by 2X. This is equal to my X. So now we can go back in and finish our chart that this is going to be 0.25 minus X, 0.25 minus X, and plus 2X. You can plug these numbers in, right? Oh, there we go. I have the X's are there, and then I lost my K value. The K should be equal to 18 once you plug in. So you would finish your E down here. You'd write out your K expression, plug the numbers in, and solve for it. And you should get that number. It is greater than 1, so it is product favored. Questions with that? When the study set, again, this is tomorrow's study set and worksheet, you'll see a percent show up. And if it's the percent change, the percent reacted, the percent decomposed, that's telling you the change. So the initial times the percent will give you the change.
Sorry, I have a question. So to find the percentage, it's the initial times the percentage that equals X.
In this case, it is because of how it's worded. And I'm pretty sure on the worksheet it's worded similar. So yeah. I'm hesitating, Major, because it's not an always. If you remember, we did nuclear chemistry and kinetics. Sometimes it would say the percent that remains. I guess that's the thing. So if this had said 68% of the iodine remains at equilibrium, then that, when we took this, that would have given us the equilibrium amount. But since it's how much reacted, it's going to give us the change amount, how much it changed by. All right. So another thing I want to mention with that, I'm not showing all the steps that you need to get full credit if this was like study set worksheet, all that stuff. And also like on the worksheet, on the celebration, you need to state this. You have to tell me this is what's going on. I did the initial times the percent. That's probably where most people lose their points. They just suddenly have all these numbers, and you need to be able that anybody could come and look at it, especially in this environment, that they could see, okay, I took the initial times the percent. And right, all right. This next part is, it goes with this question. So back here at 25 degrees, this is my K at 25 degrees Celsius. So that temperature was important. What happened now at the higher temperature? So as I increase the temperature, the value of K decreased. So this is the saddest part about being online. And this is really, to me, the saddest part, because it's really up to you and in your heart that several of you have written me these long emails about, oh, I'm going to med school and it's really important I get into med school. Is it? What's most important is that you learn how to use your brain and that you can think through it rather than just being able to flip through your notes and find a similar problem. So it doesn't really matter. It matters that you have logic skills and that you can think through stuff. So at a higher temperature, is this exo or endo? If K decreases as the temperature increases? Well, heat is shifting it. As we add heat, it shifts reversed because K decreases, right? This lower K means that it shifted reverse. Because what K is telling you is it's a ratio. In all honesty, are you ever going to see K again in your life? Some of you might, depending on what you go into, but you're all going to have to use your brain, use your heart, like think. So see, that's what you're doing here. So it's shifting in the reverse direction with heat. So heat must be on this side. If heat's on the product side, it's exothermic. So since high temperature shifts it reverse, heat's a product, it's exothermic. That's why Le Chatelier's is one of the best things we do, because you have to think a little bit. Or you can just sit there and flip through your notes and say, oh, let me just find another question like it. It's really a disservice that we've done by keeping everything online so long. All right, this one, it's really nice. And this is back to a question, Juan, you were asking me yesterday. So sometimes delta H is given to you point blank. Whenever delta H is given to you, it's telling you for the forward reaction. What this is telling you, I wrote the heat in the equation. It's before the arrow. So this is endothermic because the heat is going into, it's being absorbed. So when heat's on the reactant side, it's endothermic. So if we add more heat, we warm it up, it's going to shift forward. Because as you add heat, that's the whole idea with Le Chatelier's. If you're adding something, you have to do something with that. So as we add more heat, it has to move in that forward direction. On this previous one, it was exothermic. So as we added more heat, it went in the other direction. It went reverse. All right. You increase the pressure. That unicorn. Unicorn pooping is an issue. All right. Keep showing up. All term. Increasing. Oh, this is a great question. What happens?
Increase the pressure and decrease the volume.
You're right. So what happens to the equilibrium? When you increase the pressure, you decrease the volume. This is the one. This is where you look at the moles. You actually look at the moles of gas, which doesn't matter on this problem because everything's a gas. And so a smaller volume means you're going to go to the side that has less. So you've moved into a smaller house or a smaller apartment. Well, when you look at this one, you have 1, 2, 1, 2. You have 2 on each side. It's the same. So for B, there's no change. And that's why I was smiling, because that drives some students crazy, because they're like, but I want it to change. It has to change. Sometimes it doesn't. So in this case, the pressure has no effect. All right, the Pegasus breathes in, so we're adding hydrogen. So hydrogen's over here. If you add the hydrogen, it's going to shift it. This is one of the ones that students will do something really weird. They're saying, okay, I'm adding hydrogen, so it's going to go this way. There is no that way. There's nowhere for it to go that way. This is why yesterday, so that was wrong. I commented, this was something that helps some students, is to put it in the test tube. It's got a wall. If it went that way, it hits the wall of the test tube and it's going to have to go the other way. The arrows are here. If you add hydrogen, it's going to go backwards. It's going to go reverse. So the hydrogen makes it go reverse. And then the last one, Bigfoot, the volume changes. Again, pressure, volume, in this case, no effect, no change. The moles are the same on both sides, so volume and pressure have no effect. All right, so E. What conditions of temperature? So up here, we determined that the dragon warming it up, we want it to warm up. So we want a high temperature because that made it go towards the CO2. So that's good. And what kind of pressure do we want? You can either circle both or it doesn't matter. Pressure and volume had no effect. So you can say no matter. Doesn't matter. All right. And then, oh, F. So I don't think I mentioned this yesterday. The only thing that changes, the only change to K again is a value. It's a numerical ratio. If we add more hydrogen, if we change the volume change will always change the concentration. And so everything adjusts, so K is a constant. However, when you heat it up, the dragon up here, heat wasn't part of our K expression. So whenever you change the temperature, the only thing that changes the K value is temperature. And I did mention that, but I didn't go over it more than that. So in this case, when we increase temperature, it shifted forward. That means we're going to increase the product. We're going to decrease the reactant. I wrote it that way because K is a product over reactant. It's a ratio. And so we're going to increase the value of K. So if you move toward the product by a temperature change, you're going to increase the value of K. If you moved toward the reactant, that would decrease it. Everything else readjusts to keep K the same. Questions? Again, we can do more of these on the study set for tomorrow, and then the lab that's due Friday, that's all it's about, is Le Chatelier's principle. All right, this last one, I am required to do a quadratic. So I wanted to mention, because a couple of people came in early, today's worksheet, there is not a quadratic on there. On today's worksheet, that two things I will remind you of, if there's a solid, we had it on the previous page, and I don't know what I did with that page. Oh well. Remember, solids don't affect it. That was actually what happened on question number 5. Or you're going to be able to do a square root like we did on the previous page, where you can get rid of the square. So this is where the people with the fancy calculators actually can run into problems, because they're not afraid of quadratics, so they have no problem. And then they forget to cross out the solids. So on worksheet number 2, on worksheet number 2, question number 2, it is a quadratic, because somebody dictates to me what I'm supposed to teach you. I avoid them on midterms, on our celebration and stuff, because So those of you, you all learned the quadratic formula. If you're a geek like me, you love doing it longhand. I actually had a student who just finished his master's in math. And he would do it the same way. He was like the fastest doing stuff in class. And so that's the quadratic formula. So basically, we'll make our ice chart, and there's no way to get rid of the square. And so you have to rearrange it. So I'm just going to go through it just briefly, and then I will leave it for you to solve, or you can always come in and walk through it with me one-on-one. So a reminder, this is how much we mix. So those are my initial. Also a reminder, if you do this in your chart, you're going to end up not getting full credit. So what's wrong with my chart right now? The 0.
Yeah, units.
We need units. So these are moles, and it does say it's 1 liter. So that is molarity. So we can just, there we go. We have a 0, so we're going to shift that way. So minus x plus 2x. And it doesn't tell me anything at equilibrium. So different from the previous one. So this is just going to be 1 minus x. This is going to be 2 minus x. This is going to be 2x at equilibrium. So that's the idea of the ice chart. So this is a question like Max had said, and I always get from students, they'll be like, I'm not understanding the ice chart. That's why you have a study set every day, because that's why I said that yesterday in my intro video, that this is the key to the whole term. For the next 3 weeks, we just keep making ice charts. And so you want to, and in all honesty, I will tell you, I think these first 2 days are in some ways the hardest, because these problems are more esoteric. We get into acids and bases tomorrow, and with acids and bases, it's easier to see the application, because we get answers of pH, and I think you've all heard of pH. Whereas these answers, it's like, what do those numbers mean? So it becomes more applicable. This intro part is just kind of how K works and stuff, and so it can be a little esoteric for students. All right, so you have your ice chart. You want to please always, the ice chart has units until we get down to where we're just working with X, and then eventually we'll put the units back in. Always state your K expression, so meaning with the chemical compounds. So the HI over the hydrogen and the iodine. And now we plug in. So we have the K was given to us. And the HI is going to be 2x squared. And this is 1 minus x and 2 minus x. So you can't do a square root to get rid of it. If you have a TI-89 or TI-Inspire or whatever, you would say solved with TI, you're going to get 2 answers. You would give me your 2 answers. Everybody's going to get 2 answers. Just in the interest of time, I'm going to make a quantum leap here. I have to find where I used to do quadratics. Maybe it's a lot. Here we go. All right, when you distribute this out, right, you get 2 minus 3x plus x squared. Right, when you do your, I don't even know how to do it the way they teach you to do it now. And then that's going to move over. This whole thing is going to move over times the 50.5. That equals, please note, this is probably the biggest mistake some people make. The 2 and the x both get squared. So for those of you who have to like work it out longhand, you would have the 50.5 times the 2 minus 3x plus x squared equals 4x squared. To do a quadratic, everything has to move to the same side, so you eventually get 0 equals 46.5x squared. And please work this out on your own. I'm just in the interest of time. Sorry, minus 151.5. And even those of you with the solve function on your calculator, it's really good to use your brain cells. You know, using your calculator cells is awesome too. So you get all those pieces. Again, for those of you without the Inspire, you just get one problem, and it's on worksheet 2 that you're going to run into a quadratic. All the other times, there's a way to get rid of the quadratic. This is your A value. Let's do this in that color. So that's your A value. The negative, that is your B value, and that's your C value. And that's where you plug it into this. Kind of remember doing that back in the 7th grade or whenever you learned quadratics. So the problem with the quadratic formula is most of us learned it in 7th or 8th or 9th grade. That's also when puberty happens, and that's why people don't like the quadratic formulas. So because you're too busy dealing with the wonders of puberty. You're going to get 2 values for x. Only one of them can be right. If you get 2 values, if one of them's negative, the negative's wrong. Otherwise, the 2.3, the larger one, is wrong. Because if you tried to plug in the 2.3 here, 1 minus the 2.3 would give you a negative value. So the answer ends up being that. But again, you would state you have 2 values, and then you could cross out the 1. And then you can plug in and, I don't know, ask for all the answers. So that's where I got all of that. Questions. Again, don't go, oh my gosh, quadratic. I didn't like quadratics. I don't like quadratics. You're going to see one, and you can always come in and walk through it with me. It's on the worksheet.